Welcome to this explainer. Okay, let's just jump right in and master Cambridge IGCSE Computer Science Networks. Now, if you're gearing up for Syllabus 0478, you probably already know that understanding networks is, well, only half the battle. The other half? Getting the examiner to actually award you the marks you've worked so hard for. So today, we're going to break down exactly how to master those core concepts and, even more importantly, how to format your answers to grab that perfect score.
So we've got to start with a really common and honestly painful hurdle. Why do so many students lose marks on network questions? Time and time again, I see students walking out of the exam hall feeling super confident, only to realize later that they dropped easy points. Why? Because they wrote generic answers. They failed to use the precise scenario constraints given in the prompt. They'll use everyday trade names instead of the proper technical terms, or they'll just dump a memorized fact onto the page that doesn't actually apply to the specific situation the question is asking about. Well, throughout this explainer, we are going to fix that completely.
All right, Section 1, Evolution of Computer Networks, from Basic Connections to Global Systems.
To really get how to answer those high-level questions, we first need to understand how these systems evolved. Picture this. It's the late 1960s. The U.S. Department of Defense funds the first working network, called ARPANET. And the reason why is pretty fascinating. Computers back then were absolutely massive. I mean, they took up whole rooms, they were incredibly expensive, and obviously extremely difficult to move. Government researchers desperately needed a way to share information without physically driving tapes between these giant machines. From that very basic setup, we saw a gradual evolution of data communication. Those old, clunky systems were continuously replaced until we arrived today. The Internet, it is quite literally a network of networks, seamlessly connecting billions of devices all over the globe, from the phone in your pocket to the traffic monitoring systems in massive cities.
Now, here's the absolutely crucial part. You need to grasp this exact Cambridge-safe definition of a network before we get into the hidden mechanics. If an exam asks you to define a computer network, you can't just say, oh, it's computers talking to each other. Nope. You need to state clearly that it is a system connecting two or more computing devices, which, remember, can be anything from a smartphone to a massive server, for the purpose of transmitting and sharing information. And don't forget the medium. You have to mention that they're connected using physical wires like high-speed fiber optics or through wireless connections. Lock that specific definition into your memory right now.
Moving on to Section 2, the OSI model framework, the invisible rules of communication.
So how do all these wildly different devices around the world actually interoperate? We need an underlying architecture, and that is exactly where the OSI model comes into play. The Open Systems Interconnection Model acts as a standard reference guide for developers. Understanding this is absolutely critical, especially if you're troubleshooting network problems. Now, keep in mind, it is a conceptual framework. It doesn't actually exist as a physical piece of hardware. Instead, it lays out a clear, standardized set of rules so that digital products and software created by entirely different, competing companies can somehow work together seamlessly over a network. It's kind of like a universal translator.
Honestly, it would be really difficult to overstate just how important this model is for making sure all these devices communicate. But here's the catch. While the OSI model gives us the conceptual rules, you also have to understand the actual physical hardware framework that makes this communication possible in the real world. Because if you don't understand the physical translation of data, that conceptual model isn't going to save you on paper, one.
Right. Section 3, Modems and Web Security, translating data and protecting it.
When we look at the physical translation of data, it becomes immediately obvious why we need a modem. Your computer, it speaks a pure digital language made entirely of zeros and ones. But traditional telephone lines, they're old school. They require signals to run as analog sine waves. They are literally speaking two completely different languages. So a modem sits right in the middle. It actively modulates that digital signal into a sine wave so it can actually travel over the line to the IP hub. Then, on the receiving end, it demodulates that signal back into digital form. Without this lightning-fast continuous translation, the internet as we know it simply wouldn't work.
And get this. Here's a pretty surprising fact. While the data transfer speeds we're used to today are ridiculously fast, it's wild to think that some people out there are still running legacy modems operating at this incredibly slow speed, 56 kilobits per second. Of course, modern speeds blow that out of the water, and we can even artificially boost transfer rates using techniques like data compression. But understanding that super slow baseline really helps you appreciate just how far the hardware has evolved.
But listen, hardware isn't just about speed, it is heavily about security. If you're dealing with a wireless local area network, you need to memorize these exact vulnerabilities. WEP, which stands for Wired Equivalent Privacy, has some massive glaring weaknesses.
For starters, a lot of vendors base web keys on passwords chosen by the users themselves, which drastically shrinks the key size. Plus, it uses static keys. That means multiple users are sharing the exact same key for long periods of time. What does that do? It makes the network highly susceptible to passive attacks where hackers can just sit back and decrypt traffic using statistical analysis. It's also vulnerable to active attacks where unauthorized mobile stations inject new traffic, or dictionary building attacks, which are surprisingly easy to pull off if you analyze enough traffic on a busy network. Examiners absolutely love testing this stuff.
Okay, Section 4, Upgrading Flawed Exam Answers, the framework for top band marks.
Now, let's talk strategy. To actually secure those top band marks we've been talking about, you need a highly systematic approach. By moving methodically through these 4 steps, you make sure every single mark is captured and you avoid accidentally repeating the same idea twice. Step 1, state the core concept. Step 2, provide evidence or data straight from the specific scenario given in your prompt. Step 3, apply scientific reasoning, meaning explain the actual mechanism of how it works. And step 4, use precise examiner wording. Never, ever use generic nouns. Always tie your answer back to the very specific constraints of the question.
Let's actually see this in the real world. Notice how a top-band answer drops the generic nouns and implements exact technical constraints. Look at the flawed answer. Networks share data and use passwords to stop hackers. It's vague, it's conversational, and it earns 0 marks. Ouch. Now look at the top-band answer. Networks share resources. WEP is vulnerable to dictionary attacks due to static keys. See the difference? It uses the precise technical terms: resources, WEP, dictionary attacks, and static keys. It identifies the context, the mechanism, and the specific risk. That right there is exactly how you secure top marks.
Finally, Section 5, the final examiner clue, interpreting prompts.
Look, all those frameworks, the modem mechanics, the WEP security data we just covered, it's literally useless if your answer doesn't directly respond to the specific command word used in the prompt. If the examiner asks you to state, they just want a simple fact, quick and easy. If they ask you to define, they want that precise Cambridge-safe definition we locked in earlier. But if they ask you to describe or explain, you absolutely must use that 4-step framework. You have to connect the mechanism to the advantage or the risk. You must map your technical knowledge perfectly to whatever command word they throw at you. So, you've got the strategic framework for network questions now. You know the technical pitfalls of WEP, and you know the precise vocabulary the examiners are looking for. But here is the ultimate question you need to ask yourself as we wrap up. Having the perfect answer floating around in your head is great, but do you actually have the timed answer writing system required to get it down on paper before the clock runs out? Think about it. How are you going to adapt these strategies when the pressure is really on?